Good day and welcome back. In this video we will explore an application of double integrals. And if you look in the section in the textbook you can find several more applications, including things related to probability density functions you might encounter later on when you take a statistics course. In this video what I'd like to do is discuss the idea and relationship between density and mass for an object called a lamina. But then at the end of the video, we'll also note kind of the motivation that this gives us for our next topic, which is coming soon. So let me go ahead and start off by mentioning that what we want to do is calculate the mass of a lamina, where a lamina we think of as a thin plate with a height of 1. And I know this is kind of an arbitrary or really kind of abstract sounding thing, but this is just giving us a nice starting point of something we can do calculations on with double integrals. So in the xy plane, I'm thinking of some region D, which is representing our lamina. And the idea is that it has height 1. And what we would like to do is determine the mass from a function representing its density. Now, the reminder when it comes to mass and density is we typically think of the relationship that mass is equal to density times volume. But this formula holds true only when we have a constant density function, where it's perfectly reasonable to have what we might think of as more of a variable density function. The density of this lamina, or this object, depends upon the location you are in. So with this being said, I'm going to go ahead and write down the formula we can use to find mass. So mass of this lamina is equal to the double integral over the region D, which the lamina occupies, and what we integrate is the density function. So we think in this case mass is going to be the definite integral of density. And just to give you a little bit of intuition, the idea, if we want it to go through details, is we take our region D and we break it up into a whole bunch of little pieces. And then on each piece we approximate what the mass will be, and then we combine those together. And those approximations, in a sense, form our integrand. Where note, our integrand is really made up of this density multiplied by the dA, and typically we would look at the dA and we would think of it as an area, but because we have a thin plate with a height of 1, this area is really going to correspond to a little bit of volume. So it is of this form volume times density, which we are summing up, so this integral does in fact calculate the mass. And in terms of those details, you don't need to worry about the intuition. It's really just, can we apply this and get some extra practice with double integrals? So consider the following example. Find the mass of the lamina that occupies the region in the first quadrant that lies below the line y equals x and inside this circle centered at the origin, with the density function x squared. And note, this is nothing more than us asking you to evaluate a double integral. We're just describing it in a slightly different way. So we have a few curves being described. We have the line y equals x, and then we also have this circle of radius square root 2 centered at the origin. So roughly speaking, something of the form here, square root 2, square root 2. So we are restricted to being in the first quadrant, below y equals x, and inside this circle of radius square root 2 centered at the origin. So our region D, which is occupied by the lamina, is a small slice shaded in blue. And note, the new concept for this topic, mass is the double integral over that region D of the density function x squared. In terms of evaluating this double integral, I see at least two very reasonable approaches. One, you could consider this region D in polar coordinates and evaluate, which we will do. Or you could think of this as one of these so-called type 2 regions, something kind of varying along these horizontal lines. So I think the easiest thing is really polar coordinates. In polar coordinates, our r values are varying from 0 to square root 2, and our theta values are varying from theta equals 0 to theta equals pi over 4. So our integral, convert it to polar coordinates, the x squared would become an r squared cosine squared. The dA is r dr d theta. The r values are varying from 0 to square root 2, and the theta values are varying from 0 to pi over 4. And if you're looking at this integral thinking it looks familiar, I agree. This is in fact the second example we evaluated in part 3 of our discussion of double integrals and polar coordinates. So I'm not going to go through and recreate the wheel again, but if you look at the completed note sheet in Canvas, I do include all of the details, or you can go back to that previous video to hear me highlight some of the key bits of intuition. And what we end up with is pi over 8 plus 1/4. And just to summarize, I want to note that kind of the key takeaway for us in this section is this idea that mass is the double integral of density when we are talking about one of these laminas whose density function is given by rho. In the book, I just want to note you will see several other things. They talk about a moment with respect to the x-axis, a moment with respect to the y-axis, both topics that I think you would encounter in something like a statics course. And then also this idea of the center of mass of the object. And because this is just a bunch more practice with double integrals, I choose not to really go into any detail here. And also, if any of the suggested problems ask you to find a center of mass or moments, I only need you to find the mass. And that's the only question I will ask you on a homework assignment, the only question I will ask you on an upcoming exam. But I do want to note that this gives us some really good motivation for an upcoming topic. So instead of having a lamina, what if we had some solid object? So I'm just going to randomly sketch something that looks like a sphere sitting somewhere in three-dimensional space. Because it's in three-dimensional space, if I knew its density function, and it would be a function of three variables x, y, and z, the question I want to ask you is, how can we find the mass? And if we think about what we did with the lamina, we evaluated essentially the double integral over that density function. So in this case, if we want to find the mass of this three-dimensional object whose density we know, we would maybe have to evaluate a triple integral, gosh, whatever that might be, over this solid E. And to learn more about these triple integrals, well, you'll have to wait until the next section. So stay tuned and take care.